Welcome! In this session, we'll explore problem number 543, diameter of binary tree. We'll break down the problem, discuss its challenges, and analyze an effective solution. Let's dive in and tackle this together. In this problem, we are tasked with finding the diameter of a binary tree. The diameter of a binary tree refers to the length of the longest path between any two nodes in the tree, which may or may not pass through the root. It's important to note that the length of this path is determined by the number of edges between the nodes, not the number of nodes themselves. For example, if we are given the root of a binary tree as input, our goal is to compute and return an integer representing this diameter. The input will always be provided in the form of a binary tree's root node, and the output will simply be an integer that quantifies the diameter. To better understand this, let's look at the first example. Here, the tree is represented as node 1 at the root, with nodes 2 and 3 as its left and right children respectively, and nodes 4 and 5 as the left and right children of node 2. The longest path in this tree connects nodes 4 and 5, passing through node 2. Alternatively, the path could also extend from node 4 to node 3, passing through both nodes 2 and 1. In both cases, the path length is 3 edges, so the diameter of the tree is 3. This is the output for this example. Now, consider another example where the tree is simpler. In this case, the tree consists of only two nodes, node 1 is the root and node 2 is its left child. The longest path in the tree is the single edge that connects these two nodes. Therefore, the diameter of the tree is 1, which is the result we return for this input. Finally, let's explore the edge case of an empty tree. If the tree is empty, meaning no nodes are present, then there are no edges to consider. As a result, the diameter of the tree is 0. This example highlights how the diameter changes based on the structure of the tree. Additionally, the problem has some constraints to keep in mind. The tree can contain up to 10,000 nodes, and each node's value will lie between -100 and 100. Key edge cases to consider include empty trees, trees with only one node, skewed trees where all nodes are on one side, and balanced trees where the longest path may pass through the root or not. These constraints and examples will help guide our approach to solving the problem efficiently. To solve the problem of finding the diameter of a binary tree, we first consider two approaches. The brute force approach relies on the basic intuition that the diameter is the longest path between any two nodes, which can be calculated by summing the depths of the left and right subtrees at every node. To implement this, we recursively calculate the height of the left and right subtrees for each node, then determine the diameter at that node as the sum of those heights. By traversing all nodes and keeping track of the maximum diameter, we can find the solution. However, this method is computationally expensive, with a time complexity of n squared. The inefficiency arises because the height of subtrees is recalculated multiple times. To address this, we can use an optimized approach. Here, instead of calculating heights redundantly, we perform a single depth-first traversal. During this traversal, we compute both the height of each node and the diameter simultaneously, using a global variable to track the maximum diameter. This approach reduces the time complexity to n, as each node is visited only once, and the space complexity depends on the height of the tree, h, due to the recursion stack. This optimization makes it highly suitable for large trees. In this problem, we select the optimized approach because it provides the best balance between simplicity and efficiency. By using a depth-first traversal, we eliminate the redundant height calculations that make the brute force method inefficient. A key insight here is that for any node, the diameter can be calculated as the sum of the heights of its left and right subtrees. Since both height and diameter can be computed during the same traversal, we avoid the need for multiple passes over the same nodes. This results in a significant improvement in performance, reducing the time complexity from n squared to n. The aha moment lies in recognizing that the problem can be simplified to a single pass computation by leveraging the recursive structure of the tree. This makes the optimized approach both elegant and highly efficient. When comparing the two approaches, the brute force method stands out for its simplicity but falls short in efficiency, especially for large trees, due to the redundant calculations it performs. On the other hand, the optimized approach is slightly more complex to implement, but it excels in efficiency by utilizing a single traversal to compute both height and diameter simultaneously. While alternatives like iterative methods using breadth-first search exist, they tend to involve more bookkeeping and are less intuitive for this particular problem. The recursive depth-first approach aligns naturally with the structure of binary trees, making it both clear and concise to implement. For these reasons, the optimized approach emerges as the most effective solution, striking the right balance between clarity, efficiency, and performance. The diameter of a binary tree is defined as the longest path between any two nodes within the tree. This path may or may not pass through the root. To calculate it, we need to determine the depths of the left and right subtrees for every node. Depth is calculated as 1 plus the maximum depth of the left or right subtree. For a leaf node, the depth is 0. Once we have the depths, the potential diameter at each node is simply the sum of the left and right subtree depths. By keeping track of the maximum diameter encountered during this process, we can determine the overall diameter of the tree. This approach, while intuitive, involves recalculating depths multiple times, leading to inefficient time complexity. To improve on the brute force approach, we can use a post-order traversal to combine the depth and diameter calculations into one efficient pass. The key insight is that we don't need to calculate the left and right subtree depths repeatedly. We can compute them once while traversing the tree. Using a recursive helper function called DFS, we can calculate both the depth of a node and update the global diameter in one step. For each node, the function calculates the depths of its left and right subtrees, updates the maximum diameter as the sum of these depths, and then returns the depth of the current node as 1 plus the maximum of the left and right depths. This eliminates the redundant calculations seen in the brute force method. The base case for this algorithm is straightforward. If the current node is null, we return a depth of 0. To keep track of the diameter globally, we use a variable that is updated whenever a larger diameter is encountered during the traversal. This approach ensures that each node is visited exactly once, and all operations performed at each node are constant time. As a result, the time complexity is O(n), where n is the number of nodes in the tree. The space complexity depends on the recursion stack, which in the worst case of a skewed tree is O(n), and in the best case of a balanced tree is O log n. This optimization is achieved by leveraging post-order traversal, which efficiently aggregates information from child nodes to parent nodes. To implement the algorithm, we use a binary tree as the input structure and a global variable to track the maximum diameter. Let's walk through an example to see how the algorithm works. Consider the binary tree with root node 1, which has left and right children 2 and 3. Node 2 further has children 4 and 5. Starting at the root, we perform a post-order traversal. First, we visit the left subtree rooted at node 2. For node 4, both left and right children are null, so its depth is 0, and no diameter is updated. Similarly, for node 5, the depth is 0. At node 2, we calculate the diameter as the sum of the depths of nodes 4 and 5, which is 0. The depth of node 2 is calculated as 1 plus the maximum of the depths of nodes 4 and 5, resulting in a depth of 1. Next, we process the right subtree of the root, which is node 3. Since node 3 is a leaf node, its depth is 0. Returning to the root node 1, we calculate the diameter as the sum of the depths of its left and right subtrees. The left depth, contributed by node 2, is 1, and the right depth, from node 3, is 0. This gives a diameter of 1 at the root. However, the longest path in this tree is between nodes 4 and 5, passing through their parent node 2. This path has a diameter of 3. The algorithm ensures that this maximum diameter is captured by considering the sum of the depths at each node. Finally, the implementation uses a helper function that recursively traverses the tree and updates the maximum diameter stored in a global variable. When applying this algorithm, we must also consider edge cases. For an empty tree, the diameter is 0, as there are no nodes or paths. Similarly, a tree with only one node has a diameter of 0, since there are no edges. In a skew tree, where all nodes form a single line, the diameter is equal to the number of nodes minus 1, as the longest path includes all edges in the tree. For balanced trees, the diameter often passes through the root but can also extend into one of the subtrees. By accounting for these scenarios, the algorithm remains robust and handles a wide variety of tree structures effectively. The solution to LeetCode problem number 543, diameter of binary tree, involves calculating the longest path between any two nodes in a binary tree. This path may or may not pass through the root. The code begins with the definition of the treeNode class, which represents a node in the binary tree. Each node has a value, val, and pointers to its left and right children, left and right. The solution class contains the diameter of binary tree method, which computes the tree's diameter. Inside this method, we initialize a class variable self.diameter to 0. This variable will keep track of the maximum diameter found during the traversal. The depth helper function is defined within diameter of binary tree. This function recursively calculates the depth of the left and right subtrees of a given node. If the node is none, i.e., a leaf node, it returns 0. Within the depth function, after computing the depths of the left and right subtrees, we update the self.diameter variable. The diameter at a given node is the sum of the depths of its left and right subtrees. We use max to ensure that self.diameter always holds the maximum diameter encountered so far. Finally, the depth function returns the height of the current node, which is the maximum depth of its subtrees plus 1, to account for the current node. The recursion starts with the root node, and the final value of self.diameter is returned as the result. This implementation efficiently computes the diameter in n time, where n is the number of nodes in the tree, as each node is visited only once. Edge cases, such as an empty tree or a tree with only one node, are handled naturally by the base case of the depth function, which returns 0 for none nodes. Here, we begin by defining the treeNode class, which represents the structure of a node in our binary tree. Each node contains an integer value, a reference to its left child, and a reference to its right child. The class includes three constructors: a default constructor, one that initializes the node with a specific value, and another that sets the value along with its left and right children. Next, we define the solution class, where the actual algorithm resides. Inside this class, we declare a private variable, diameter, to keep track of the maximum diameter of the binary tree as we traverse it. The main method, diameter of binary tree, takes the root node of the tree as input. It calls the helper method depth to calculate depths recursively while updating the diameter. Finally, it returns the maximum diameter computed. The depth method is a private helper function designed to calculate the depth of each subtree recursively. If the current node is null, it simply returns 0, as there's no depth to calculate. Otherwise, it computes the depth of the left and right subtrees by recursively calling itself on the left and right children. Once we have the left and right depths, we update the diameter by taking the maximum of the current diameter and the sum of these two depths. This step ensures that we're always tracking the longest path between any two nodes in the tree. Finally, the method returns the height of the current node, which is the maximum of the left and right depths plus 1. This height is crucial for computing the depth of parent nodes higher up in the tree. Here, we're working with a simple balanced binary tree. The root node is 1, with 2 children, 2 on the left and 3 on the right. Node 2 further has 2 children, 4 and 5, while node 3 has 1 child, 6, on its right. To calculate the diameter, we first initialize self.diameter to 0. Then, we call the helper function depth starting at the root node 1. The depth function will recursively calculate the height of the left and right subtrees for each node while updating the diameter. Starting with the left subtree of node 1, we process node 2. For node 2's left child, node 4, since it has no children, the depth function returns 0 for both left and right subtrees. This means the height of node 4 is 1, and the diameter remains unchanged at 0. Similarly, for node 2's right child, node 5, the height is also 1, and the diameter is still 0 at this point. Now, combining the results from node 4 and node 5, we find that the height of node 2 is 2, since it is the maximum of the left and right heights plus 1. Here, the diameter is updated to 2, which is the sum of the left and right heights of node 2. Moving to the right subtree of node 1, we process node 3. Its left subtree is null, so the height is 0. For its right child, node 6, since it has no children, the depth function again returns 0 for both left and right subtrees. The height of node 6 is 1, and the diameter remains 2. Combining these, the height of node 3 is 2, and the diameter stays 2. Finally, for the root node 1, the left and right subtree heights are both 2, giving a total diameter of 4. This is the maximum diameter of the tree. The function then returns 4 as the final output. In this example, we are working with an unbalanced binary tree where node 1 has only a left child, node 2, which itself has a left child, node 3. The process begins similarly by initializing self.diameter to 0 and calling the depth function at the root node 1. Starting with the left subtree of node 1, the depth function processes node 2. Within node 2's left subtree, we find node 3, which has no children. Therefore, the depth function returns 0 for both its left and right subtrees, making the height of node 3 equal to 1, and the diameter remains 0. Returning to node 2, its right subtree is null, so the height is 0. Combining these results, the height of node 2 is 2, and the diameter is updated to 1, which is the sum of the left and right heights of node 2. For the root node 1, its right subtree is null, so the height is 0. The total diameter is calculated as 2, which is the sum of the left and right heights of node 1, and this becomes the final output. In this final example, we have a binary tree with just a single node, 1. Since this node has no children, the depth function returns 0 for both its left and right subtrees. The diameter calculation at this point remains 0, as there are no paths between nodes. The height of the tree is simply the height of the single node, which is 1. Since there are no other nodes to consider, the diameter of the tree is finalized as 0. This is returned as the final output, representing the absence of any paths in the tree. The time complexity of our solution is O(n), where n represents the number of nodes in the binary tree. This is because our recursive depth function visits each node exactly once. As it traverses the tree, the function performs a few key operations at each node. First, it makes 2 recursive calls to calculate the depths of the left and right subtrees. Then, it uses these depths to compute the diameter at the current node. Finally, it calculates and returns the height of the current node. Since these operations are constant time, O(1), and every node is visited only once, the total time complexity scales linearly with the number of nodes, resulting in O(n). Whether the tree is balanced, skewed, or consists of just a single node, the number of nodes dictates the time complexity, making this consistent in the best, average, and worst cases. Now, let's look at the space complexity, which is O(h), where h is the height of the binary tree. The main contributor to space usage here is the recursion stack. The depth of the recursion stack corresponds to the height of the tree. In the best case, with a single node tree, the height is 1, and the space usage is O(1). For a balanced tree, where the height is approximately log n, the space complexity becomes O log n. In the worst case scenario, with a completely skewed tree where all nodes form a single branch, the height of the tree equals the number of nodes, n, leading to O(n) space complexity. Importantly, no additional data structures are required for this solution, as all calculations are performed in place with the help of the self.diameter variable. This ensures that the overall space usage is minimal, depending primarily on the tree's height. To further understand the efficiency of this approach, let's compare it with a naive solution. A brute force method might calculate the depth of the left and right subtrees for every single node independently, resulting in a separate traversal for each node. For a tree with n nodes, this would lead to an O(n)² time complexity, as each of the n nodes would need to process its subtree. In contrast, our optimized solution combines the computation of depth and diameter into a single traversal. By reusing the depth information obtained during the recursive calls, we reduce the time complexity to O(n). This makes the solution significantly more efficient. Mathematically, the recurrence relation for the time complexity is T(n) equals T(n_1) plus T(n_2) plus O(1), where n_1 and n_2 represent the sizes of the left and right subtrees. Since these subtrees together contain n1 nodes, the recurrence simplifies to T(n) equals O(n). The space complexity remains O(h), as the recursion stack depth is determined by the height of the tree. This combination of reduced time and minimal space usage demonstrates the optimality of the solution. Let's talk about some common mistakes people make when solving the diameter of binary tree problem. First, a frequent issue is computing the depth multiple times for the same nodes. This often happens in brute force approaches where the depth of subtrees is recalculated repeatedly for each node, leading to redundant computations and an inefficient solution with a time complexity of n squared. The fix here is to use a bottom-up approach, which allows us to calculate both the depth and diameter in a single traversal. Another common mistake is not handling edge cases properly. For instance, if the tree is empty or contains only one node, overlooking these cases can lead to incorrect results or runtime errors. To address this, you should explicitly handle scenarios where the root is null or the tree has just one node. Lastly, there's often confusion between depth and diameter. Depth refers to the distance from the root to a leaf, whereas the diameter is the longest path between any two nodes in the tree. Mixing these concepts can lead to incorrect calculations, so it's crucial to clearly distinguish between them and validate your approach accordingly. Now, another common pitfall is not considering the path that passes through the root. The diameter of a binary tree doesn't always lie entirely within the left or right subtree, it could span across both subtrees and pass through the root. Ignoring this possibility can result in an incomplete solution. To fix this, ensure that your calculation for the diameter includes the sum of the depths of the left and right subtrees at each node, and then compare this value with the global maximum diameter. Additionally, having an incorrect base case in your recursion is another frequent issue. If your recursion doesn't return 0 when encountering a null node, it can lead to runtime errors. To prevent this, always check for null nodes and return 0 as the base case in your recursive function. Moving on to interview insights, the most efficient approach for this problem is to use depth-first search with post-order traversal. This strategy allows you to compute both the depth and the diameter in a single pass through the tree, making it highly efficient. When implementing this approach, it's important to keep in mind the trade-off between time complexity and space complexity. The optimal solution achieves a time complexity of n, but it requires h space for the recursion stack, where h is the height of the tree. Also, it's essential to clarify the problem's requirements with your interviewer. For example, does the diameter count the number of nodes on the path, or the number of edges? This distinction can significantly impact how you implement your solution. Finally, be prepared to explain the intuition behind your approach. Interviewers often value your ability to clearly articulate your thought process just as much as the correctness of your code. As you practice, you may also encounter related problems such as binary tree maximum path sum or maximum depth of binary tree, which share similar concepts and techniques. Let's wrap up by discussing some alternative approaches. The brute force approach involves calculating the depth of the left and right subtrees for every node and then computing the diameter. While this method is simple to implement, it's inefficient for large trees due to its time complexity of n squared, caused by redundant calculations. A more efficient alternative is the optimized DFS with post-order traversal. This bottom-up approach calculates both the depth and diameter simultaneously during a single traversal, achieving a time complexity of n. Although slightly more complex to implement, it's highly efficient and avoids unnecessary computations. Another option is to use iterative DFS or BFS. These approaches are less common but can be useful to avoid recursion stack overflow in very deep trees. However, they require additional bookkeeping to track parent-child relationships, making them more challenging to implement and debug. Despite the trade-offs, these alternatives can be helpful in scenarios where recursion limits are a concern, particularly in languages with restricted stack sizes. Great job! Today, we covered the problem diameter of binary tree, discussing its key concepts and approaches. Remember the importance of recursion and tree traversal in solving such problems. Stay curious and keep challenging yourself with new problems. Thank you for joining, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!